Hello and welcome everyone. Welcome back to the another solution for our problem of the day. Just write down yes or no in the chat box if I'm clearly audible. Oh guys, think my voice is clearly audible. Okay, thank you Rishit. Hi. So today's problem of the day is a basically okay. Hi everyone. So let me share my screen and I'm expecting that today's problem of the day was like solved by everyone. And if you are not able to solve it, don't worry. You will learn a new algorithm. Okay. So today's problem of the day is BFS of a graph. It is the like BFS and DFS are the building blocks of graph and let's say tree data structure. Okay. So everything can be solved using graph and using BFS DFS for graph and tree. Okay, so basically you will be given a directed graph, and what you have to do, you have to find out the breadth first traversal of the graph. Right, so how will we find the BFS? So over here will be given the directed graph. Okay, so just let me open my one note. Okay, so let's start. It does not matter if the graph given to you is a like directed graph or the undirected graph. Okay, so BFS algorithm remains same for each and every graph. Okay, so there is a minor difference in the breadth first search which you can apply for uh, what do we say, for a directed graph. So one thing we need to just handle it, like we need to take care that whether the graph contains a cycle or not. Okay, so generally in a directed graph, we can expect that there are no cycles present in the graph. So okay, so basically let me draw one of the graph, and I'll be teaching you how to apply the breadth first search algorithm. Zero, 1, 2, 3, and this is 4. Okay, so over here, now let's imagine this is the graph, and each and every time I'll be applying the breadth first search algorithm from the 0th node. Okay, so how does the BFS algorithm work? So BFS algorithm works radially. Radially, by what does it mean by radially? So basically, if you imagine this as a tree, so BFS algorithm will travel level wise. Okay, and the other name for breadth first search is level order traversal as well. Okay, during the traversal, if you are exploring each and everything that's encountered at the same level, that means at each and every point, let's say you are reaching all the nodes, let's say after uh, if imagine this is your starting node. Okay, this is your starting node, and how, like how far is the node number 2 from the starting node? I can see the node number 2 is at a distance 1, right, from the starting node. How far is node number 3? How far is node number 1? All of them are at a distance 1. So in BFS, all these nodes 2, 3 and 1 will be encountered at the same time. Okay, so that is what BFS algorithm means. So how will we apply breadth first search algorithm? So BFS is very simple. So for breadth first search algorithm, we need a queue data structure. Okay, and what else do we need? After queue data structure, we need a visited array. So I'm explaining the general breadth first search algorithm in which we are using a, let's say, visited array. If the graph given to you is a DAG, that is directed acyclic graph, that means there will be no cycle. So in such kind of graph, there is no requirement of visited array, right? So over here, it is not mentioned that the given graph will be a DAG. So I'll be using a visited array. And what will be the size of this visited array? It will be equivalent to the total number of nodes. Over here, the nodes numbering starts from 0, and there will be a V number of nodes. Okay, starting from 0 till V. So over here there are 4 nodes. So I'll be creating a graph. I'll be creating a visited array, boolean visited array, and its size will be equivalent to total number of nodes. I can see 5 nodes are there over here, right? And this is my queue data structure. So what I'll be doing, first of all, I'll be inserting the starting node inside my queue data structure. So 0 will be inserted. Okay. Now what I'll be doing? Now, after inserting a node, I'll be removing that node from the queue, and I'll be inserting all the neighbors of the removed node inside the queue. So now I have inserted 0. So I'll be removing 0. And simultaneously, you will be marking the node which has been visited, or the node that is being removed from the queue as visited. Okay, so basically, whenever you insert a node inside the queue, you will be marking it as visited. Is it clear till now? Was it clear to everyone? Yes or no in the chat box? A quick response from everyone. A quick yes or no in the chat box. Okay, thank you for the confirmation. So now over here in this breadth first search algorithm, whenever you insert a node inside the queue, don't forget to mark it as visited. Okay, else you will be like sometime it is possible that if there is a cycle present inside this graph, then this BFS algorithm will run infinitely. Okay, so in order to handle it, whenever you insert it, do not forget to mark it as visited. So true. 0 has been marked as visited. Now I'll be removing 0 from the queue, and I'll be printing it in the uh, output. So now 0 has been removed. So for the removed node from the queue, what you have to do? You have to insert all the neighbors. How many neighbors are there for this 0? I can see 2 is the neighbor, 3 is the neighbor, and 1 is the neighbor. So only insert those neighbors which are not visited. So I have not visited 2, right? Because its boolean value is not true inside this visited array. So I'll be inserting 2. And what else do I need to insert? I need to insert 3 because it was not visited. And what else I need to insert? I need to insert 1. So over here, you might ask a question, like a doubt might arise in your mind that, see, what if I inserted 3 first, I inserted 2, and in this manner? What if I inserted 1, 3, and 2? So basically, it depends upon how elements are inserted inside your adjacency list. Okay. So in what manner the elements have been added for the respective node inside the adjacency list. When we insert into queue, we mark as visited, right? Yes, we mark it as visited. So all this 2, 3, and 1 will be marked as visited. Okay, so that's very important. So this 2 will be marked as visited, 3 will be marked as visited, and 1 will be marked as visited. So let me write down the important point. Whenever you insert a node, mark it as visited. So sometimes if you forget how breadth first search algorithm works, then this is the area in which you will be facing difficulty, like when to mark it as visited, because you will be inserting the there are 2 operations which are being performed on each and every node. One will be inserting inside the queue, and the other one will be removal, right? So basically you will be encountering the nodes twice. Each and every node will be encountered twice inside this BFS algorithm. So now 2, 3 have been inserted. So basically you can observe all this are at the same level, right? And they are present inside the queue at the same time. So now again the same process, remove one by one from the queue. So 2 will be removed, and what I'll be doing, I'll be printing 2. So now I'll be inserting all the neighbors of 2. I cannot see any neighbor of 2, right? So nothing will be done for 2. So now the next node will be removed, that will be 3. So remove 3 from the queue, and insert all the neighbors. I can see only one neighbor, and that is also not visited. So insert it and mark it as visited, right? So 3 has been removed. So now the last node for the level, and this one will be removed, and it will be printed in the output. So how many neighbors of 1? None of them, right? So this edge goes from 0 till 1. So nothing is no one is neighbor of 1. And now I have encountered each and every level, right? So again I'll be doing the same process. Again, remove the number. 4 will be removed from the queue, and insert all of its neighbors, but 4 does not have any neighbor, and this is your BFS breadth first traversal for the given. Yes, the graph is a directed graph. Okay, So this is our BFS traversal for the given graph. Breadth first search. Any doubt in this part, any section? Or else we'll be moving to the algorithmic part. Okay, I'll be writing down the steps of the algorithm. So you guys can take the reference whenever you are trying to implement the BFS algorithm. Okay, thank you for the confirmation. So just let's quickly write down the algorithm. And just a minute, let me reopen this. Okay, so the algorithm is pretty simple. You just need to, I'll be mentioning the very critical areas in this algorithm where you should like take utmost care. Okay, so the first critical area of this BFS was insert a node, mark it as visited. Okay, so now what I'll be doing, first of all, I'll be needing a queue data structure, right? So I'll be taking a queue, and what else do we need? I need a visited array. So take the visited array. Now what I'll be doing? So first of all, there is a, for any traversal you need the starting point, right? So I'll be inserting 0 as my starting point. So you insert 0, that is the starting node. I'll be writing down start instead of 0, or you can take it as 0. So insert 0 inside the queue, and whenever you insert it, do not forget to mark it as visited. So mark 0 as visited, mark visited for the starting node. This is the starting node and it has been visited, right? So now what I need to do, now you can start applying the BFS algorithm. Now here is our actual BFS algorithm. So what I'll be doing, if you observed carefully, that how many times was I running this loop, like how many times I was removing the element from the queue. I stopped when the queue was completely empty, right? So I'll keep on removing the elements from the queue when the queue is completely empty. So what I'll be doing, while the queue size is, or you can say while the queue is not empty. Okay, so while the queue is not empty, let's imagine there is a function that will return true or false. Okay? So while the queue is not empty, I'll keep on removing the elements from the queue data structure, right? So over here, one thing we need to take care is that I have a different implementation of BFS. Okay, so over here, what I'll be doing, I'll be working on each and every level of this. So what I'll be doing, first of all, I'll be removing the size of the queue data structure, and this algorithm, this implementation will be helpful to you in future as well. So I would suggest you should follow this implementation, that is working level by level. Okay, so I'll be removing the size. If what is the meaning of removing the size, if I remove the size of the queue at any instant, so that means that this that many number of elements are the part of the same level. Okay, and I'll be iterating over the size. So what I'll be doing, I will be removing size number of elements from the queue. While the size is greater than 0, that many number of elements will be removed. Okay, so let's say current is removed from the queue. One element will be removed from the queue, and what I'll be doing, I'll be exploring all the neighbors. So what I'll be doing, I'll be iterating over the neighbors of current, or let's say there is an adjacency list. Inside the adjacency list, there will be a list containing the neighbors of current node, right? So I'll be iterating over all the neighbors, and I'll be inserting it inside the queue. So what I'll be doing, I'll be only inserting if I find that this node is not visited. So if the node is not visited, then what I'll be doing, I'll be inserting it inside the queue. So just insert it, queue.add, and along with the insertion, what do you need to take care of? I need to mark it as visited neighbor is equal to true. So mark the neighbor as visited. And here is the end of our algorithm. So when should you print the element? When should you print the element? So whenever you remove the element, print it in the output. So over here, we are going to write down our logic in a function, right? As we're writing the logic in the function will be returning something, right? So it will be returning a list containing the elements of our BFS. So over here, I'll be add the element to the list. Let's say I'm calling the list containing BFS of the graph as an answer list. Okay, so I'm naming that list as my answer list. So over here, this is our answer list, and you can print the element, you can print the current element over here, or you can add it to the answer list. Okay, so this is the section where you will be printing the element. On removal of the element, you print the element. Okay, and on insertion, you mark the node as visited. So these are the two critical, like let's say critical section of this algorithm where you should take care. Okay, is it clear? Yes or no in the chat box if this part was clear to everyone. And then we'll be jumping towards the implementation part for the same. Yes or no in the chat box, a quick response from everyone. Could you repeat the uh, two section again? Okay, so I'm saying that what you need to take care of whenever you insert the element, mark it as visited, and whenever you remove the element, you should print the element. Okay, so do not confuse yourself between this. So whenever you remove the element, print it in the output. Okay, so that is how the BFS works. So on insertion, you don't need to print it. So whenever you remove the element, that means you have to print it in the output, and whenever you insert it, mark it as visited. Okay, okay, Rishit. So now let's quickly write down the code for the same. I'm writing down the code in Java, but you can take the reference of the algorithm and code it in your own language. Okay. So first of all, what else do we need? I need an answer array list, right? So I'll be creating an answer list. And what else do we need? I need a queue data structure. I have a queue data structure. I have an answer list. And what else do we need? I need a Boolean array. And what will be the size of this Boolean array? It will be total number of nodes. How many nodes are there? V number of nodes are there. So the size of the visited array will be equivalent to V. Now, the starting point. Which is the starting point according to this question? BFS star result starts from the 0th node. So I'll be inserting 0 inside our queue. Queue dot add 0. And as I'm inserting a node, mark it as visited. Okay, so now what I need to do? I need to iterate over the entire queue. If the size of the queue is still greater than 0, that means some elements are present, right? So I'll be first of all remove the size of the queue, and I'll be iterating over the size number of like elements will be removed. That means the entire level will be iterated. So now just remove the element. So let's call it as current queue dot remove. Can I take array list instead of linked list? Implementing queue. Okay, so the array list won't be efficient because the insertion and removal in a linked list will be in order of one. Okay, and that is what provides you the uh, better implementation of a queue. So integer current is queue dot remove. So I have removed the current element, and I'll be finding out all the neighbors. So what I'll be doing over here, I have a list of lists. That is an adjacency list is provided. So what I'll be doing, I'll be iterating over the elements of the adjacency list. So this is a for each loop. Okay, adj dot get, that means the list, that is the list of current element. I'll be iterating over all the neighbors. If the neighbor is not visited, then first of all insert it inside the queue and mark it as visited. Right, so this is our entire. And one more thing we need to write down is that insert the element inside our answer list, right? So current, whenever you remove, insert it inside the answer. And at the end, here is our end of the while loop. What I need to do, I need to return the answer list, right? So let's see if we are getting any kind of error. The compilation was successfully done, and let's try to submit it. And what about the time and space complexity? What do you think? What will be the time and space complexity of this? So the time and space complexity of this algorithm is going to be order of v plus c, because each and every time you are not like each and every node will be visited only twice. That means once when it will be inserted inside the queue, and the other will be removal of the queue. Right? So they will be inserted and removed. Two operations on each and every queue. How many on each and every node? How many nodes are there? A v number of nodes, right? So the time complexity will be order of v. And what about the space? So space complexity can be considered as order of what? What will be the space complexity? So in worst case, you can take that the space complexity will be order of v. The reason is that at any instant, let's imagine a graph in which there are only two levels, the starting node and all the nodes are present at a single distance from the graph. So that means at any instance, v number of nodes are going to be there inside your graph, right? So time and space complexity of our BFS algorithm is order of v. Yes, Rishit, exactly. So I hope you really enjoyed this session, and uh, do like this video, okay, if you really enjoyed. And there will be something interesting coming up from tomorrow, and do not forget to watch tomorrow's video, okay? So thank you everyone, thank you for watching, and do like this video, share it with your friends, and do subscribe to Geeks for Geeks practice channel. It was great interacting with you guys. Bye bye, have a good day. I mean good night. Bye bye.